Hi everyone, welcome to the video presentation for this week. Today we're talking about atmospheric stability, which you can also think of as atmospheric motion. The atmosphere is constantly in motion, that's both horizontally and vertically, and especially the vertical motion of the atmosphere. If a section of air is caused to rise or sink, that can cause weather phenomena to occur, such as cloud formation or even precipitation. So this is our final lab on the atmosphere, and with the concepts that you will learn this week in lab, and you've already been learning in lecture, you'll understand the basics of how weather forecasts are made. To review, the temperature profile of the atmosphere is there are some unique peaks at different altitudes, such as the ozone layer in the upper stratosphere causes an increase in temperature. And in the thermosphere, it gets warmer as you go up. However, for all intents and purposes, weather events are always located in the troposphere. And throughout the troposphere, temperatures decrease as you go up. That's not new material. You've learned that before. But keep this in your mind as we go forward, because the actual environmental lapse rate, or the temperature at different heights, this actual temperature profile of a particular location, can vary somewhat. It's not a perfectly smooth line. So now, like I said on the first slide, the atmosphere is constantly in motion. It moves side to side. We have winds, horizontal winds, and air parcels can move up or down. Closest to the surface, the air is the thickest. There's the highest density air, and that's just related to gravity. The heavier parcel of air or heavier mass of air sinks. And this is just related to buoyancy force, balancing out the gravitational force. And understand that the pressure decreases as you go up. Hotter air also wants to expand, which can influence the pressure in that way too. However, we're going to learn about some unique processes called adiabatics, in which we make an assumption that there's no heat transfer from the outside air to an air parcel. Think of an air parcel like a parcel of land, in that it's defined by us. It might not have any real world meaning. There might not be a line on the ground to delineate a land parcel. Same as an air parcel, there isn't any real definable boundary. But for the sake of understanding these stability concepts, we'll be using this term to just mean like a mass of air, or think of also like a box of air that doesn't interact with the surrounding by changing temperature, but that box or parcel would want to expand based on the pressure around it. So what causes the motion of air parcels? Well, a lot of things. The most simple examples are the orographic effect, which basically means if wind is moving over a mountain, say, or a hill, that air is forced up over the land, so that's called orographic lifting. Convergent lifting is basically when two near surface winds or air parcels would collide, and the only place that they would have to go is up. They can't go down due to the ground, and two winds are both converging on each other, which causes lift. It's also convectional, or related to heating of the surface. If there's a parking lot, that's going to warm up really quickly in the sun, and that parking lot, say, could be anything such as bare soil, rock, would heat the air directly above it. But as you go further up, the air is affected much less by that, say, parking lot, so that uniquely warm parcel near the parking lot or surface gets heated up really quickly and wants to expand, and when it expands, it wants to rise. There's also frontal lifting. Basically, when two fronts collide, the warmer front tends to move over the cold front. So the warm air would rise. That's called frontal lifting. So when lifting occurs, the process of that air parcel expanding as it rises involves an adiabatic process, which is a concept from thermodynamics. And to best describe this, I like to think of if you've ever used compressed air or a spray can and you've held the trigger down for longer than a few seconds, your hand feels really cold. The can itself gets very cold. And this is due to initially the gas inside the can or liquid, whatever's inside the can, is at very high pressures. And as you press down the nozzle, that pressure is released. And when that pressure decreases, temperature decreases. So that's why if you've ever used compressed air or something on your keyboard, your hand gets very cold afterwards. That's an adiabatic process. Now, in reality, just the act of holding the can allows a heat transfer from your body back into the can. So the definition of adiabatic is actually involving no exchange of heat with a system and its surroundings. And that's how we need to understand these concepts. But in reality, there is some heat transfer. Now, air and gases don't exchange heat very easily relatively to, say, like a can. So this still holds true, these adiabatic processes for air parcels. They work better for that. So, okay. So on the last slide, we talked about the ways that a parcel may be forced to rise or lift. Whatever the reason, when that parcel rises, there's less pressure exerted on it from all sides just due to the air getting thinner as you go up in the atmosphere. So that parcel expands out. When it expands, it cools. The rate at which it cools is pretty much very well defined. Basically, it depends on the humidity of that parcel or the whether that air parcel is saturated or unsaturated. Now, this is going back to a couple labs ago, the humidity concepts. Remember, relative humidity is just a measure of the total water holding capacity of air versus how much air is actually in it. So if there's 100% relative humidity, the air is completely saturated. So the rate at which this parcel rises is called, or cools as it rises, excuse me, is called the lapse rate, which is given in degrees per distance, so such as Celsius per kilometer. And for unsaturated air, meaning the humidity, relative humidity is less than 100%, the rate is about 10 degrees of cooling for every kilometer that you go up or that you increase in elevation. So the interesting rate is the moist adiabatic rate, the MAR. This is for saturated air. So that means that the relative humidity is already at 100%, aka the air is holding all of the water vapor that it can. So what's unique about the MAR is that it's cooling still as a saturated air is still forced to lift for whatever reason. But because when you cool things, remember the holding capacity for water vapor decreases, so that water gets pushed out of the parcel and it has to condense or form clouds, precipitation, etc. But you may be asking, why is the rate of cooling -6? Uh, you know, it's a slower rate of cooling than -10. That's because of latent heat that's given off when gaseous water as a gas, gets forced out of the parcel and it has to condense to be liquid. When that happens, remember, there is latent heat given off. So that latent heat goes somewhere. Well, it goes back into the parcel itself. So that makes up the difference of 4 degrees per every 1,000 meter. It's that latent heat that causes the difference between the NAR and the DAR. So that still may be a little confusing. I know it's kind of some abstract physics here, but let's just work through a simple example just to review so we're all prepared for the lab this week. So imagine there's this parcel of air sitting down at the surface. It's pretty warm. It's 32 degrees C. And then for whatever reason, it's caused to initially rise. So this parcel down at the bottom rises to 1,000 meters. And when it does that, it cools. Now, in this example, we're assuming that the initial parcel had less than 100% relative humidity. So we use the dry adiabatic rate of 10 degrees C for every kilometer or every 1,000 meters. So we go from 32 degrees C down to 22. Okay, now say this parcel is still continued to rise. It continues to rise up to 2,000 meters in height in the atmosphere. And when it does that, it expands a little bit more, and thus it cools. And it's still not completely saturated with water, so it cools at 10 degrees C per 1,000 meters, and our parcel cools to 12 degrees. Now we do this again. It rises another 1,000 meters to 3,000, and it gets down to 2 degrees C. Now, at this point, we don't really have this information, but basically they would have to tell us what the initial dew point was or relative humidity, so we know how much water is in the air. But in this example, at this point, 3,000 meters, the relative humidity hits 100%. So if that parcel is forced to rise any more, and in this example it does, it rises up to 4,000, then 5,000, that water gets pushed out because just due to the holding capacity of air for water, the saturation point decreases. So everywhere above this lifting condensation level, we call, or basically just the height at which you switch over from the dry adiabatic rate to the moist or wet adiabatic rate. The point that you switch over is just called the lifting condensation level, and that's you can see this outside if you were observant and you see that there's a particular point, or if you live near the mountains and air is forced to lift orographic lifting, you can see this in action. You can see that clouds may start to form at a particular height, a set height with a lifting condensation level. And if air is still forced to rise above that lifting condensation level, clouds continue to form because the water is still getting pushed out. And when it gets pushed out, it condenses and forms clouds. If it is pushed out very quickly, you have precipitation. You'll have huge cumulonimbus clouds. So notice here, above the lifting condensation level, the air cools a little bit slower. Remember, that's 5 or 6 degrees per every 1,000 meters due to the latent heat given off from that condensation forming. So stability. Now, the lab today is called atmospheric stability. Basically, stable means for an atmosphere, the parcel resists rising on its own. It just wants to sink, or it wants to stay where it is. It doesn't want to rise any further. What may cause a parcel to be unstable? Well, that could be due to if the parcel is warmer than the surrounding air. So warm things rise. Think of a hot air balloon. Hot air balloon is filled with really hot air and it wants to rise. That's what causes the hot air balloon to lift off the ground. So you may think of the hot air balloon as initially unstable. It wants to rise. But at a certain point, there will be equilibrium reached and the hot air balloon or parcel may become stable again. So stability depends on the conditions that you have initially. It also depends on what the parcel temperature is relative to the surrounding air temperature is. So just like the hot air balloon example, the temperature inside may be warm, which causes it to rise. But if it's a really, really hot day, that temperature difference might not be as great. So the stability of the atmosphere is caused by the initial conditions, but also the environmental conditions. So throughout across the Earth, there's very different environmental lapse rates. It's not a straight line like we might think, as the troposphere decreases in temperature as you go up, but it's not the same rate for every place on the Earth. So that might be due to weather, climate, time of year, a lot of things. So, but we can measure this. Scientists can measure this with atmospheric sounding, weather balloons, weather stations. So we can figure the environmental lapse rate out. And we're going to be basically working through some parcel examples. What would happen if a parcel is forced to rise, and whether we can call that the condition stable or unstable. So you'll see a graph similar to this on the right here. Basically, the slope of the blue line is the MAR. The slope of the red line is the DAR. So the slope of the temperatures on the x-axis, the slope of the moist adiabatic rate is, say 6 degrees for every 1,000 meters versus dry adiabatic rate 10 degrees for every 1,000 meters. So let's look at this example. Can we call these conditions stable or unstable? Just take a minute and look at the parcel temperature and look at the environmental temperature and predict whether this is stable or unstable. These conditions would be stable. This arrow on the right of the graph actually shows us that the tendency of the parcel wants to sink, which means that the conditions are stable. And how else could we figure that out? Well, if you look at the parcel temperature, initially it's 25, and the environmental temperature is also 25. But as you rise up to 1,000 meters, notice the environmental temperature now is 20 degrees C, but the parcel cooled at the dry adiabatic rate, which is 10. So you subtract 10 from 25, and the parcel is now 15. So 20 of the surrounding air is warmer than 15 of the parcel. So the parcel wants to sink, or it wants to stay where it is. It doesn't want to rise any further. There are other ways that you can think about stability too, based on the environmental lapse rate, which the environmental lapse rate is, like I said, affected by a lot of different things, including the human-built environment, because buildings, concrete, parking lots, they create a lot of warmer air, and sometimes inversion layers can occur. This is very common in heavy urban environments that may prevent air from rising off. Now, this could cause smog to be trapped over a city if that smog, or the pollution isn't able to disperse, because it might be trapped by a warmer layer above, far off the ground. Now, I don't want to get too far into the weeds on this, but want to just expose you to that. Like these concepts can be applied to weather all over the world and so many different weather-related phenomena. So that's why stability and instability of the atmosphere are really important. Now, if you've heard of the concept of rain shadows before, this is also related to this same concept of adiabatic cooling and lifting condensation level, orographic lifting. All these concepts build to what we would call rain shadows, which means, say if you have, let's look at the example on the right. So on the right I have circled the Cascade Mountains in Washington. They go down to Oregon and Canada. And generally, the air pretty much always blows from west to east in Washington. So the wind is bringing moist air off of the Pacific Ocean, and it's relatively flat until you hit the Cascade Mountains, at which point that wind wants to go over the mountains, and it's forced to rise due to orographic lifting. And when it does that, clouds form, and lots of rain may occur, so that water that's in the air gets forced out, so the air becomes drier. And then after you go over the mountains, after the air goes over the mountains, then the air starts to warm up again, just due to the parcel shrinking again as it goes down in elevation. But it doesn't gain any of that water back. So the air is now drier than it was on the west side of the Cascade Mountains. This is really evident too in the Himalayas, which is the image on the left. That's what's circled, the Himalayan range. Now, to the south, generally there are monsoon events, which monsoon just basically there's tons of rain and precipitation for a particular part of the year, and that's due to the wind shifts and coming off of the ocean, moist air again. As that moist air hits the mountain range, Himalayas, which are super tall, we have the same effect happening. The orographic lifting, there's lots of precipitation and cloud formation on the windward side of the Himalayas, or the south side. And then as you go north, you hit the Mongolian Plateau. It's steppe. It's very dry because the air was already dried out from the condensation due to orographic lifting. So the point being is that these concepts apply all over the world, and they affect things like climate. They have impacts for farming, human life. So keep that in mind too. As you work through the lab today, there will be an example of orographic lifting, just like I went through. If that's still confusing, just shoot me an email. We'll also work through a parcel that could be forced to rise, not due to orographic lifting, just what happens as the parcel rises and expands and cools. And this will be our last lab on the atmosphere. So we're going to be switching gears going forward. If you have any questions about this material, of course, please, you can email me or message me, and I can help you through the lab this week.